Hello, my name is Joram van der Sluis, and I am presenting this work also on the behalf of my colleagues, Ewout Paul and Dario Gavrila from the Intelligent Vehicle Group at the TU Delft. We have done an experimental study with existing 3D detectors based on LiDAR and possible camera sensor to evaluate their performance on persons, meaning cyclists and pedestrians. More than half of the 1.3 million road fatalities yearly worldwide involve vulnerable road users, VRUs, which include pedestrians, cyclists, and other riders. Vision-based VRU detection is meanwhile incorporated in active safety systems of various premium vehicles on the market. To allow for higher levels of automation, detection performance needs to be significantly upped. LiDAR is an attractive sensor that can directly and accurately measure distances and can deal with low light environments. It can add robustness to vision-only detection. Therefore, we present an experimental study on LiDAR-based 3D person detection. First, we perform a more in-depth analysis that goes beyond the leaderboard results. Where do the 3D localization errors come from? Secondly, we show results on the new EuroCity Persons 2.5D dataset, a significantly larger and more diverse dataset than the current point of reference, the KITTI 3D Person dataset. Lastly, we perform domain transfer experiments between KITTI and the new EuroCity Persons 2.5D dataset to see how these datasets relate to each other. For the methods, we select two top-performing methods that had their software available at paper submission time. We chose one representative that uses as sensor modality LiDAR plus image and one that uses LiDAR only. Other differences between the methods are the number of stages and the bounding box regression targets. AVOD is a two-stage network, while PointPillar is a single-stage network. AVOD regresses to a four-corner model, including heights and orientation, while PointPillars regresses to the 3D center point, length, width, height, and orientation. Let's turn to the performance metric. A 3D object detector outputs predictions as 3D bounding boxes, which are represented by 7 values: an X, Y, and Z position, a width, length, and height, and an orientation along the ground plane. During the evaluation, true positives are determined by checking for each predicted 3D bounding box whether it has sufficient overlap with a ground truth 3D annotation. Specifically, one looks at the intersection over union, or IOU, as indicated in the figure and formula. Perfect overlap will have an IOU of 1. No overlap means an IOU of 0. In the KITTI 3D object detection benchmark, a detection is deemed a true positive if the IOU is larger than 0.5. Obviously, a true positive depends on both the accuracy of the predicted center point as well as the predicted extent of the bounding boxes. We will investigate how much each contribute to the overall performance. So, how do the methods perform on 3D person detection? This graph shows the error in 3D bounding box center position and extent for different IOU thresholds. Each of these errors is measured in meters. We can see that the largest errors are made in estimating the width and length, also referred to as depth, of the bounding box. We also notice that the smallest error is made in estimating the X and Z position, or in other words, lateral and longitudinal position. Let us now look at the 3D box center localization error on the ground plane. How does it vary over a certain IOU range? The graph on the right plots the lateral and longitudinal error of the detection. It is a top view of the detections on the ground plane. In blue, you can see the detections which have an IOU above 0.5. These are the detections that are considered correct by the current metric. The orange points show the detections with an IOU between 0.1 and 0.5. Now, some numbers. Of the blue points, 98% of them have a Euclidean error of less than 15 centimeters, as indicated by the circle. One can argue that a localization error of less than 15 centimeters is quite accurate. Of the orange points, another 73% have an error of less than 15 centimeters, which would increase the number of true positives by 23%. This is also reflected by the average precision. At a lower IOU threshold, the average precision is much higher. So basically, we could get a much higher headline performance number in terms of AP3D if we relax the IOU threshold used. And we would still have a quite accurate center position localization. So far, we considered the KITTI 3D object detection dataset, which has so far been the point of reference in the community. However, in terms of numbers of persons, it's quite small, as can be seen in this overview table of datasets, in the one before last column. It contains only 9,400 pedestrians and 3,300 riders. Other large datasets have appeared more recently, such as Waymo, NewScenes, Argoverse, and Lyft. We choose to perform our additional experiments on the novel EuroCity Persons 2.5 dataset, which is introduced at this conference. It is one magnitude larger than KITTI in terms of pedestrians and riders combined. And equally important, it is arguably the most diverse dataset available, with recordings over 12 countries, 30 cities, in all seasons, day and night, and with different weather conditions. It is also worth pointing out that persons in the ECP2.5D dataset are not blurred, similar to KITTI, which minimize the introduction of any undesirable bias in any image-based detection method. To get some insights in the KITTI and ECP2.5D datasets, we plotted the position of each ground truth annotation with respect to the ego vehicle. These are top-down plots where the vehicle is positioned at the origin. Each pixel in these plots indicates an area of 1 by 1 meter, and the color indicates the number of ground truth annotations at that position, using a logarithmic color coding. The leftmost plot shows the pedestrian distribution in KITTI. You can see that most pedestrians are quite close to the ego vehicle. The plot next to it shows the pedestrian distribution in ECP2.5D, which shows that a far large number of annotations. In this plot, one observes a band of lower person density running from the bottom to the top of the plot, right in front of the vehicle, at 0 lateral distance. This is to be expected, as pedestrians will be less likely walk within the vehicle path. Another observation is the higher pedestrian density on the right side of the vehicle, which is the outcome of right-side traffic on European roads, with pedestrians on the right pavements closer by and less occluded. Finally, let us consider the evaluation of our two methods, PointPillars and AVOD, on KITTI and ECP2.5D. We consider both the case of training and testing on the same dataset and the case of domain transfer, where we train on one dataset and test on the other. This is a busy table, so let me guide you through it. The table rows relate to the training set used and whether LiDAR intensity was used in addition to 3D point cloud information. The table column relates to what test set was used. One observes following results from the table. First, as shown in bold, the best performing network for each dataset is PointPillars, with intensity information trained on the corresponding dataset. This shows that there is relevant information in the LiDAR intensity. Second, performance on ECP2.5D is consistently lower than on KITTI for both PointPillars and AVOD, indicating that this dataset is more difficult than KITTI. Third, the best cross-dataset performance is found in PointPillars, trained without intensity. So while there is relevant information present in intensity, it presently does not carry over to another dataset. Here we show some typical detection results on the EuroCity Persons 2.5D dataset using PointPillars. The image is shown for reference only and is not used by PointPillars. It depicts a scene from Barcelona. In this frame, green boxes represent ground truth locations. Yellow boxes represent true positives. False positives are shown in red. They include the back of a scooter and a traffic pole. The one false negative in this frame is shown in purple. Due to the low number of LiDAR points on this pedestrian, it is not detected. Let us now summarize the findings of our experimental study on 3D person localization. PointPillars clearly outperformed AVOD with a 3D average precision of 68% versus 53%, and 33% versus 27%, on respectively the KITTI and ECP2.5D dataset. The new ECP2.5D dataset is one order of magnitude larger than KITTI in terms of pedestrians. It is tougher due to a larger portion of distant persons with fewer LiDAR points. Whereas the headline 3D average precision results might seem low, 3D box center localization accuracies are in fact quite high. AP3D errors mostly relate to 3D box width and length. KITTI and ECP2.5D have quite different biases. Cross-domain training and testing leads to significantly decreased performance with an AP3D decrease of at least 6.8%. This leads us to the future work. Improving cross-domain adaptations for 3D object detectors is essential, as one will want to reuse existing collections of dataset annotations when faced with a new sensor release. We thank you for listening. If you are interested in more of our research, please visit our website or view our YouTube channel.